Welcome to another Leetcode problem discussion. Today's problem is problem 1 to 7, word ladder. This is one of the problems within the blind 75 list. So without further delay, let's see the problem description. So what we have here is we will be given a string or word, the begin word, and also another word, the end word. And the third thing that will be given is a dictionary word list. So what we have to do is we have to create a transformation sequence from the begin word to the end word, okay? And in the transition state, there might be other words. So some of the conditions are all these transition word as well as the end word, right? They have to be in the word list that is captured here, okay? And the final word is the end word. It's not necessary for the begin word to be in the dictionary. And then the next condition is how do I find two adjacent word? So what is the condition for that? So every adjacent pair of word differs by a single letter. So that means the difference between this begin word and S1 is a single letter. Also, the difference between S1 and S2 is a single letter. Okay, so how do we solve this problem? Okay, so I think the best way is if we start with the one example. So let's start with example 1. So the begin word here is hit, and the end word is cog. And as you can see, the end word is already in the dictionary. So this is the dictionary or word list given. Now let's find, let's try to determine the adjacent word with the begin word. So as you can see, the begin word is hit. And an adjacent word to this word is a word that has only one letter difference. So as you can see, this word, we're just inspecting by naked eye, right? So as you can see, hot, if you just replace this I with O, then these two becomes adjacent words, right? Okay. And then from hot, you can see that we can change just one of the letters D to dot, right? So that is another adjacent word of hot. From dot, we can go to dog, right? You can see that just by changing this T. So these two are adjacent. From hot, we can also go to lot, okay? And from lot, we can go to, so you can see here, from lot, we can go to log. And from log, we can go to cog. Not only that, even from dog, we can go to cog. Okay. And also from log, we can go to dog, or from dog, we can go to log, right? Similarly, from lot is an adjacent word of dot, right? So as you can see, we have denoted the adjacency here with these lines. And now you can see that clearly this is a graph. So this is going to be a graph problem where each of the words, the begin word, the end word, or other words in the dictionary are actually nodes. So each of these are nodes, and these are the edges. So these are the edges between the nodes, right? Okay. So our problem is we have to find, so if this is a begin word and this is the end word, what we have to do is we have to find the smallest number of steps, right? So that is important, the smallest number of steps. So we have to traverse, first of all, we have to somehow create this graph, and then we have to traverse it to find the smallest number of steps. Well, if we traverse it using just any traversal, say DFS, right? The traversal may go like this, right? Like this. But that's not actually the smallest number of steps. The smallest number of steps here is going to be, so one example of the smallest number of step is this, and then this, right? So there'll be 5 words involved, right? Okay. So the best traversal strategy here is BFS, because BFS, instead of going into the depth, BFS first goes level by level. That means it goes to the neighbors first. Okay, so let's try to solve this problem. If we want to use BFS, obviously we want to use BFS. First thing that we need is a queue, right? We need a queue. And inside the queue goes the word, the begin word. We will put the begin word inside the queue. And the other thing is we have to keep track of how many words have been, how many levels have been traversed so far, so that we can retain the number of steps, right? So hit is going to be word 1. Okay. Now, next what we have to do is we have to traverse the graph and we have to explore the neighbors. So how do I discover my neighbors, right? So obviously what we can do is we can uh, transform hit into a array of characters, right? It will look like this, array of characters. And then we select one index and change it to everything from A to Z, right? So if I replace H with A, it becomes something like this, AIT, right? And but this word, we cannot just jump to AIT. We have to find if this is a valid word, right? Okay. So for that, let's keep a dictionary. Let's keep a hash set. That's the easiest way to check fast that if this AIT is a valid word or not. So in the hash set, what you want to do is we want to put everything, say hot, and then dot every word in the hash set, every valid word, dog, lot, log, and then cog, right? We put everything there. And we are trying to change this first character, right? And as you can see, none of the first character changes will take me to a valid word. But what will happen is next time when we try to change the second character, we'll get something like this, hot. And hot is obviously a valid one, right? A valid character, a valid word. So next what you do is we have taken hit out, right? Hit out. And then we can put hot as the next word. And we increase the level by 1. So that's the next one, right? Okay. So hot is the next adjacent word I can put in the queue. And another thing is like, how do I make sure next time I take hot out, right? I take hot out. So once I take hot out next time, I will try to find the adjacent word to hot, right? By doing the same thing, by changing each of the characters to all characters from A to Z, right? So, and there is a, and as you can see, hot may go back to hit, right? Because if I change this one to I, this will go back to hit. So how do I make sure that I don't have a cycle in my traversal? So for that, I will keep another hash set, say visited. So every time I put something in the queue, I immediately put it in the visitor. So initially we had put hit in the queue, and then we had put hot in the queue, right? So I put it in the visitor. So next time when hit actually hot changes to say hit, it not only checks here, it also has to check here. If any of these are true, it won't put it into the queue. Okay, so that way I am making sure that I'm not putting making a cycle. Okay, so from hot, as you can see, I can change to dot. Dot is obviously a valid word, so I check here, and dot is obviously not in the visited list. So it's not in the visited list and it's a valid word. So next, what I have to do is I can put dot here into the queue with this, right? Okay. And not only just dot, hot can also change to lot. So I once I put dot into the queue, I will add it to the visited list. The hot can also change to lot, right? And I put lot into the visited list. I put lot here with level 3, right? Okay. And that's the only 2 words that will qualify. Okay, next. So I have got dot, I have got lot, right? Okay. So every time I take any word out of the queue, say I take dot out of the queue, right? Dot out of the queue. I have to check if this is the end word. So my end word is, say, my end word is cog, right? So I have to check. First thing that I have to check if this is already the end word. If it's the end word, I just return this, right? Okay. So obviously dot is not cog right now, is not equal to cog. So next what I do is I do the same thing. Just I want to keep on changing of dot. So as you can see, from dot, if I can change to uh, I can change to lot, right? So dot can change to lot. So basically it can change to lot. But the thing is, although lot is a valid word, but lot is already visited. So I don't put lot again in the queue. That's important, right? But from dot, you can see I can change to dog. Dog is a valid word and dog is still not in the queue. So next what I'm going to do is I have to put dog here. I will put back dog with value 4 because I will increase this to 1, right? So I'll put dog, and so this is going to be dog, right? Okay. So dog goes into the queue. Next, from dot, I think we can't go anywhere. So next what I have to do is I have to take out log, right? So every time, this is important, from every level, I will take only the ones that are in the same level. I will take only those out of the queue, right? Okay. So I have to keep track of the size of the queue. So from the log, you can see we can obviously from log, I can go to, oh, sorry, not log. I took out lot. So lot can change to log, as you can see. Log is a valid word and log is still not in the visited list. So I put it in the visited list and put it into the queue. So log goes with 4. Okay, so these 2 are the next ones. So next time the queue size is, I know, 2. So I make sure that I take 2 items out of the queue. So dog, first I take dog out of the queue. So I take dog out of the queue. I check if it's cog, no. And then from dog, I start making changes. And at one point you can see I can get to cog. Cog is in the hash set, right? And cog is still not visited. So I add cog here. And then I add cog back here with value 5, right? Okay. Then from dog, I can get to log. Well, log is obviously in the hash set, but the thing is log is also here in the visited. So I can't push log into the queue. Okay, so that's it. From dog, we cannot change to anything else. Okay, next what I have to take out is log, right? So I will take, as I said, like we in the 4th level, we are taking 2 items out. So I take log out and then log changes to cog, obviously. But the cog, this is in the hash set in the word list, but it's already visited. So I don't put cog again here, right? Okay. So I don't put it again here. The only thing remaining is now is cog. So I take cog out. I check if cog is equals to cog. Yes, right? If that is the case, what I do is I just return this as my result. Okay. Okay, so there goes my problem description, explanation of the problem. For the second example, you can see the begin word and the end word are the same. The only difference, and the word list, the only difference is this time you can't see cog in the word list, right? So what will happen is, since the end word is not in the word list, the end word never goes into the queue, right? So the queue becomes empty, but we'll never find the end word. So in that case, we have to return 0. Okay, so let's talk about the code. Initially, we'll have these hash set words, which contains all the words in the dictionary. So what we do is we read from the dictionary, we read from this list and add them to the hash set, right? Okay, so this is used to look for the valid words. Okay, next for the BFS, we need a queue. And obviously inside the queue, there goes the word and its level, right? Because we have to retain the level to see how many steps we need or how many words we need to reach the end word. And then we put into the queue the begin word with its level as 1. This is the first word. And then we need another hash set to keep track of the visited words so that we can avoid the cycle. And since we have added this begin word to the queue, we also mark it as visited. And then our BFS starts. So we keep on doing this until our queue is empty. And we know at every level, we have to take everything out of the queue, right? So we'll be adding to the queue in the intermediate levels, but we don't want to take them out together. So this is, I showed you in the explanation, right? So we have to strictly, this is for BFS, we have to make sure that we just take out of the queue level wise. So whichever words have a level of 2 should be taken out together. Level 3 has to be taken out together. Okay, next we get the queue size, the current queue size, and then we run a for loop. So every time we will just take one word out for that level, and then next what I do is we take it out, and then we this is a pair that we are taking out. So the key is going to be the word itself, and the level is going to be the value. After I take it out, first thing I have to check if it's already matches the end word. If that is the case, I just return the level, right? That is the number of steps. If that is not the case, then what I do is for each so for each index of the word, right? So if the word has this length, I will, for each index, what I'm going to do is I'm going to change the character in that particular index to everything starting from A to Z. Okay. Okay. So first I will just convert the whole word, the taken out word, to a character array, and then run a for loop, which will run 26 times. And the current index is I. So what I'm going to do is I am just going to change the ith index character to this C, right? Okay. And then convert it into a string and see if this newly formed word is a valid word. So that means I will check if this is a valid word, and if it's a valid word, if it's not visited in the past. So let's make this in the other order, that will make more sense. So first I have to check if this is a valid word. That's not only enough, we have to check, make sure that this valid word is not visited in the past. If that is not the case, I add that new word to the queue, increase the level by 1, and mark it as visited. Okay, so I will keep on doing this, and at certain point, if I hit my end word, then I will return the level. If that is not the case, if I run everything here and it's still the queue is already empty and I haven't hit my end word, that means the end word is not reachable, in that case, I return 0. Okay. And what is the time complexity of this algorithm? So let's say m is the length of highest length of word, right? If m is the highest length of word and n is the number of words, as you can see, adding them to the hash set of word list takes order of n time. But the space that we need is order of mn, because every word can be of size m characters and there are n word from there, right? Okay, so this space might be order of mn. The time we'll take is order of n here. And then, as you can see in the queue, since we are using a visited list, we are making sure that every word just goes in the queue just once and is popped once, right? So this while loop is going to run order of n times. Okay, inside that, you can see that what we have to do is we have these. Okay, so including this for loop is order of n times, because we're making sure that this in this for loop a queue element is taken out, and in total there will be like order of n elements taken out. Okay, so next, once I take an element out, I will run another for loop here, and that for loop will run to the length of the word. And as we know, the highest length of the word is m. Okay, so this for loop will run m times, and this for loop, and inside the for loop, what we are doing is we are just selecting one index and replacing that character of that index from A to Z. So this one is running 26 times, constant times. And but the thing is here, once I change the index and make it a new word, this thing is order of m. So overall, this one is going to run order of m squared time, right? So overall, this is going to take order of m squared, right? And this is just for one word, right? This order of m squared work is being done just for one word, so we will do it for n words. So in total, it is going to be order of m squared n, right? So that is going to be the time complexity. So the time complexity is going to be order of m squared n into n. Okay, and the space complexity is we are using this word list hash set, this hash set for keeping all the words, and also another hash set we're putting it there. Say this is visited, so this is also, this may contain in the worst case, or not in the worst case, this may contain like all the words, so that's also order of mn. And also this queue may in the worst case contain like all n words, so that's also order of mn. So the space complexity is order of mn plus order of mn and mn, so it's order of m into n. Okay, so that's it. Thank you very much for watching. We will come back with another video next time.